So the 2.6 worksheet, I'm just grabbing a sheet of paper here. So the 2.6 worksheet, question number 3, I do want you to do it in Desmos. And when it says find a regression equation that best models the data, I'm wanting you to let me know, is it linear and what is it? And is it exponential and what is it? So you're going to do your 2 models. So you have to put in your data here. So what t values would we put in if our base year is 1970?
Like 0, 10, 20, 30, 40.
Excellent. And 40, right? Yep. And
Yep.
so this would be your X1 in Desmos, and this would be your Y1 in Desmos. And then your percents that come out are whole percents. They're already in percent form, so you don't have to put these. Stephen asked about this last week. You don't have to put in 0.047, just put in 4.7, 6.2, 8, 10.4, and 12.8. Yep. And if you want to put that in, I don't mind waiting here just a minute. So, yeah, so for this data here on the US, the percentage of the US population that's foreign born, we go ahead and put our data in, and you're right, it kind of looks like it could be either. Right, when we do our graphing here. And what did you say about exponential, Carter, if it's exponential?
That it multiplies, but then also for linear, doesn't it make a straight line?
Yeah, but I mean, I could kind of see both going on here. I mean, it kind of looks like it's curving here, but then it kind of looks pretty straight. So how did we decide in 2.8 last week? How did we decide between the two? Remember that big problem we did on the US population? I think it was a population one where we had to decide which was better fit. Stephen, if you want to chime in, you're welcome to chime in.
Yeah, wasn't it the correlation coefficient?
Okay, so you have to check both models and decide which one has the best correlation coefficient. So let me know when you get those in, Carter. I'll be right back.
Your lines of best fit. It'll pop up after that. It's the R.
So is I think my Desmos is still showing, right?
Yeah.
So if we do Y1 tilde, the MX1 plus B, that gives us the parameters for a linear model, and then the R, the correlation coefficient. Do you see that, Carter?
Yeah. Yep.
And then let's look at I want to wait till you tell me that you got that one in, okay?
Let me do the other one.
Pardon me?
1 sec.
Okay, no rush at all.
Okay. I got the other one.
Okay, you got the exponential in too?
Yeah.
Okay, so the exponential is A times B to the X1, right? And on the exponential, we have to always make sure that we click on the log mode box or we won't see the R. And if you have the log mode box clicked on and off, you can see that the A and B changed slightly. So it's important that we are using log mode. Okay, so now when we do these, They both look like they kind of fit pretty well, but which one fits better?
I feel like yeah,
You feel what, like which one?
I don't know. I feel like it's really close, but maybe the exponential.
You chose the exponential. And what, did you use the picture or the correlation coefficient? What was your choice?
I'm using the like the line, like
The line that the model makes?
oh wait, don't you go off the correlation coefficient?
So more than likely you would use the correlation coefficient. They're both very, very, very good fits. So on this one, I could see where a student, you could choose either as long as you gave me good reasoning why you chose it. And it doesn't even it says explain your choice. I don't give you that much room to explain your choice. But if you told me the correlation coefficient is better for the exponential model, but I think the linear is really realistically how it's growing in our country, because just like that, the population, the US population one that we did in 2.8, I mean, it could kind of go either way. I think that was the one that could kind of go either way. And we end up choosing linear, right? Was that the one in 2.8? I can't remember which one we said was actually a linear fit. Or tuition costs, maybe that's what it was, right, for 2.8. So on this one, I think you could choose either, but I want to make sure that everybody knows that it's based on the correlation coefficient is usually how you would choose that.
And it's the one that's closer to 1%.
Yep. Yep.
Okay.
And it's barely closer, right? I mean, it's not, it's 4 thousandths closer. So it's not that it's that much closer, but yeah, you're right. And for those watching, if this is all making sense and you're understanding, oh, I put in one model and I put in the other model and I use my correlation coefficient and I'm choosing which one is better, that is the gist of unit 2. You could feel pretty confident, like, okay, I'm getting this. This is good. This was referring to question number 3 on the 2.6 worksheet. Any other questions on that worksheet? Or the 2.7 for now. I think so I'm going to go ahead and go back and share my screen, and I'm going to spend some time going over the unit 1 review for folks at home so that everybody can get out their unit 1 review. And because I did not give feedback in JetNet, which I'm happy if you email me, I'm happy to give that feedback or meet you on Zoom and go through those with everybody. And Carter, I'm happy to do that with you too. I forgot. I kind of did that with, but you should see when I go through these, what ones. So on the first one, the key here is it's the new minus the old over the old, or the new minus the original over the original. These two have to be the same. And so it's a very large number, which feels weird. And then turning it into a percent feels even more weird. So your interpretation should be talking about this context here. So there was a 2,800% increase in federal minimum wage from 1938 to current. And really, that's not even the current anymore, is it? Well, it's pretty much about $15 to $20 is the minimum wage now, right? Because you can't get anybody to work for under what the the government's paying as far as unemployment goes. So, any questions on that one? So number 2, like I said, I'm gonna go kind of quickly through these. Number 2 was asking for you to find the percent discount. So that means we had to find the amount of money discounted. So we saved $140 out of the $299.99 original. So my discount was 46.7. Okay, question number 3. We gave you this little sales sign that would be displayed at the store on this Dyson lens here, and it says they want us to calculate the original price. So because $15.69 is the price that we're paying, we have to use the percent that we are paying, right? And so we're paying 42% of the price because it's 58% off. So the percent that we're paying is equal to 1 minus the 0.58, which is 0.42. Okay, and then we have to divide by that 0.42 to get $37.36. And whatever you get, you could take 58% of that and subtract and make sure that you got back to the sale price. And you wouldn't if you did the wrong percentage. And that's how you should double check your work. The next one, many people gave me the number of the calculation of both. So this was the females. And then I forgot to write down the males. So the number of males was 176. Minus the, so we'll make this a 4, right? And so there were males was 164,397. And then how many degrees make up the sector? So many of you told me the percentage, but it's taking the percentage of female, which is 0.07, and multiplying by 360 degrees. And I came up with roughly about 25 degrees in my pie. And then there were various reasons for letter C. And letter C, I just put because I used a rounded value in the pie chart, so it wasn't going to be exact. Okay, number 5 on the unit 1 review B, letter A, I wanted you to tell me that this is spending in millions of dollars, because that's going to lead you to how to answer B correctly. Because it says, which year was the highest spending, 2011, and what was the amount? And so you needed to tell me it was 700, it was 700 billion, because this is in millions. So if you estimate it 211, so you would be just under this. So you would either write this and write millions, right? Or you could write 700 and then just write the word billions. So either of these, or you could write it out, any of those. And then it says describe the trend. And so you're just going to let me know how you visualize what was going up as far as it was increasing, then kind of dipping, but then going back up again. Okay, the next one is doing some unit exchange with Bitcoin, US dollars, and then the euro. And so we had an exchange for Bitcoin to US dollars and from the euro to Bitcoins, but not the euro to US dollars. So we just practice writing out some conversions here. And then it says convert US dollars into Bitcoins, which we can do. So if you put your dollars in the denominator, they cancel out and you're left with Bitcoin. And so that was 3.15 Bitcoins. And then letter C, some of you wrote down the exchanges, but you didn't know what to do with it. So we're going to start with what we were given, the 1,200 euros, and I'm going to multiply by the Bitcoin to 1 euro that we were given. So my euros cancel. But then I also need to get rid of Bitcoins because we wanted US dollars. So I had to use my US dollars to 1 Bitcoin. And that translated into about $1,346.02 for going from euros to dollars. Then question number 3 was similar in kind of the making as the one from the worksheet where we had to find out how many, I think it was like 5K races. So this is how many inches are in a 5 kilometer race. So I know I'm starting with 5 kilometers. I need to get to inches. And there's a couple different ways you could do that. This is the way I chose. I canceled out my kilometers into miles. And then to cancel out my miles, I use my feet. And then to cancel out my feet to get to inches, because inches is overall what I wanted. And then when we multiply straight across, we get 316,800 over my 1.61. And when I divide, depending on, like I said, you might have been just a little bit different than mine, and I didn't count it wrong because of the little bit different strategy on your exchange. Any questions from my live folks here?
Oh.
And then number 8 says a model of the Space Shuttle Challenger has a scale of 1 inch on the model is the same as 64 inches on the actual Challenger. And that gets a little confusing because in real life, we know that 12 inches equals a foot. So that's not what we're saying. We're saying that, oh, I don't have my bobblehead here. I have a little bobblehead that represents a real life scale. Just 1 minute. Let me see if I have my son's. Oh, darn. Dang, I had a really cool from a Disney cruise that we went on. I wanted to show. Anyway, so model and actual is how I lined it up. So the model is 1 inch for every 64 feet of the actual size of the Challenger. And they told us that the actual Challenger is 122 feet. So I know that I just did a scaling up kind of a thing that we did in unit 2, but there's a couple different ways you could do it. So I said 122 divided by 64 is 1.906. And so 1.906 times 1 is 1.906. So that's the model. It's 1.906 inches. Number 9 is all about our relative change again. So don't mind my work. The actual difference is right here. We're taking the new, which is the times 13 debt, and we're subtracting the 1971. And this is where I think some folks at home are trying to do things by hand. So I'm going to go ahead and just 1 minute here. I'm going to save this work. Oh, geez. I'm going to save this work as worksheet 2.6.3. Okay. So I'm going to go to my Desmos here for y'all and share with you how I would do this one. And it is going to be helpful here because I have to put my whole scientific notation in parentheses. So I've got 1.7824071380733382 times, so star 10, and then I'm going to make that go to the exponent of 13, right, parenthesis. So I want that whole number for 2014 to stay there, and then I'm going to subtract my 1971 number in parentheses, which was 3.981297444555 times 10 to the 11th. Okay, so there you have it. So because one had an exponent of 13 and one had an exponent of 11, we still have a difference of times 10 to the 13th. So that's my actual difference right there. And then if I take that, I'm just gonna go and put parentheses around the whole thing. And then I'm gonna just divide. So divide, and I'm dividing by this 3.98 thing. And then I get 43.76. And then that note there is my relative increase is 4,377%, 4,377% increase. Crazy. And that's what you were going to interpret on letter C, is telling me that between 1971 to 2014, the US national debt increased by 4,377%. Okay, then question 10, we're getting very close to being done. So question 10, going back to my, oops. Oh. Going back to my paper here. So question 10 was asking you if Michigan's House has 110 seats, which it does, and this much was our population in Michigan, what would be our standard divisor? That's essentially what it's asking. What would be our perfect divisor if we could divide up the population evenly? And it would be 90,563.6 people per representative. I rounded down because you can't round up. You don't have enough people to round up. So if all things were perfect, for every representative, there would be, or for every 90,563 people in the state of Michigan, we would get one representative. But in all reality, that doesn't work because you can't divide up your district. So you have exactly 90,563 people here, and then exactly 90,563 people here. So if you go to this website here, it says some districts have as low as 77,000 people per district per representative, and some have as high as 91,000 people per district. And so they said calculate the relative error using the estimated maximum. So my error is a 91,000, and I'm subtracting what it actually should be, right? This should be what it is perfectly, divided by what it should be perfectly. And so it comes out to be 0.48%. So the website overestimated by 0.48%. And it's not really the website overestimated. It means like that's really how it is. If we use the maximum number of people in some of the districts, they're over by 0.48%. Any questions? And then last but not least is the question on the standard divisor, using the standard divisors. And so this one said there are 15 seats. I got to portion those over 7 districts, and the standard divisor is 64,000. I gave you that. And so here are my 960,000 population of people split up into my 7 districts. So district 1 has 125,000 people. And A said, explain how the values for the standard quota were calculated. Well, I wanted you to explain how did we get to 1.95 right here for district 1. So not how did I get to 64,000, how did I get to my standard quotas? So it's by taking your population of the district and dividing by your standard divisor, 64,000, I get 1.95. Then B says use Hamilton's method to determine the number of seats. And this is what you would have gotten because you had to write out your lower quotas and upper quotas. My lowers were only 11, but I had 15 seats to give. So I wrote over here that I had 4 too few, right? I had 4 extra to give out. And I gave those because my starred districts had the highest decimal values. So 0.95 was first. And then 0.88 over here was next in district 7, then 0.67, district 3 was third, and then district 5 with 0.59 was last. So they got the extra, they got to round up. And then letter C says, why is apportionment used to assign seats to each district? Most of you answered it perfect because you can have part of a person, or so that every district gets a fair share, something like that. Any other questions for my live people over the unit 1 review?
Yeah, I have a question.
Okay, sure. What's that?
So when you went over the number 9 for the cumulative versus national debt, when we show the difference, you want us to write like the times 10 to the exponent.
Right here?
Yeah,
Oh, yeah, because if you don't, it looks like there's only a difference of 1.7. Right?
okay,
So if the 10 to the 13th tells you that it's just a really ginormous number, and if it were 10 to the 3rd, it would only be times 1,000, right? 10 to the 3rd is 1,000, but it's 10 to the 13th, and so it tells us that it's in the trillions.
gotcha.
Mhm, mhm, sure. Any other questions over the unit 1 review?